Okay, last thing we had on the board was where we started drawing space-time diagrams, and we considered the world line of a particle which is force-free, which has a straight world line in space-time. We considered an accelerated particle which has a curved wave line, a world line, and we considered the light ray. This was the last thing, the light ray. So that was our x0 coordinate, x1, x2, and x3 always in the head. And we found that light rays, according to the postulates of special relativity, should move under 45 degrees with respect to the vertical and on straight lines. So now we can consider the set of all light-like, we can consider all light signals which pass through a particular event A. So this would be the set of all straight lines which have an angle of 45 degrees with respect to the vertical. And I think it's geometrically fairly obvious that this gives a cone. Well, actually it's a hypercone, because what looks like a circle, this cross-section which looks like a circle, is actually a sphere because of the missing dimension. And that's what we call the light cone of A. So the set of all light signals through an event A make up the light cone. And that's absolute. Yeah? It's the same thing in all inertial systems. So all observers agree what is a light cone. I mentioned already that this is far from self-explaining, because if you think of light signals as emitted from a light source like little bullets, then we would expect that the shape of this cone depends on the motion of the emitter, of the light source, right? But special relativity claims that this is not the case. Light always propagates in the same manner, independent of how the light source is moving. So that's far from trivial. But if we accept this, and we will accept this, then we get this light cone as an absolute element in our space-time. And we can write down the equation for this light cone. We can write down the equation which events which lie on this light cone on the boundary have to satisfy. So the equation for the light cone is obviously the following, where for each point which is on the light cone, the temporal distance to the event A must be the same as a spatial distance if I multiply the time with c as we always do it. So here we plot not t, we plot ct, right? Then the angle is just 45 degrees. It doesn't look like 45 degrees in my drawing, but it's supposed to be. And then this length should be the same as this length. And I can write down this equation. Obviously, this means that if I denote by A0, A1, A2, A3, the coordinates of the event A, then the temporal distance squared must be the spatial distance squared. So this must be the same as x1 minus A1 squared, x2 minus A2 squared, plus x3 minus A3 squared. And that's the equation of the light cone. Yeah, the set of all events x, events capital X with coordinates x0, x1, x2, x3 that satisfy this equation lie on the light cone. So where obviously A0, A1, A2, A3 are the coordinates of A. And this equation is supposed to hold in any inertial system. So it's not particular to the inertial system we have chosen. Obviously, the light cone splits into two halves. That's obvious from the picture, a future half cone and a past half cone. So the light cone, do I write it with a hyphen or without? I think without. The light cone divides into future half cone Yeah, this should be written with a hyphen. So that's the set of all events x which satisfy this here, and in addition, the inequality that x naught is bigger than a naught. Yeah, so with respect to the time coordinate, it lies to the future of the event a and past half cone. X naught smaller than a naught. So this here is a future half cone, and this here is a past half cone. Okay, and because this is an absolute element, it gives a decomposition of the space-time in an observer-independent manner. So we can classify now, with respect to this event A, we can classify all events according to whether they are inside the cone, outside of the cone, or on the boundary. And there's a certain terminology for this, which we will use often. We say this is only meaningful for events x which are not A. So the event A itself lies neither in the inside of the cone, nor in the outside, nor on the boundary. Because, well, it lies on the boundary, but on this very special point here. So we exclude the point A. So we say the following, that x is time-like, light-like, or space-like, with respect to A. So it's not an absolute characterization of the events x, it's something which is done in relation to a particular chosen event A. And this is true if this expression here, if I take this to the other side with a minus sign, then it depends on whether this expression is negative, positive, or zero. Right? For light, if it's on the boundary, so if the two things can be connected by a light signal, then it must be zero. If it's inside, it must be, well, have one side. And if it's outside, it must have the other sign. So this expression here, if I take this to the other side, x naught minus a naught square plus x1 minus x1. Oh, board is a little bit too short. X2 squared. Let me continue here. Is smaller than 0, equal to 0, or bigger than 0. So it's called time-like. If it's negative, this means it's this term. If the temporal term gives a bigger contribution than the rest. If it's light-like, if it's on the boundary, if the two things are equal. And it's space-like, if this is bigger, this means that the space-like part is bigger than the time-like part. So this means I have here inside the events which are time-like with respect to A, here also. I have here in the outside the ones which are space-like with respect to A, and I have here on the boundary the ones which are light-like with respect to A. Yeah, of course, this is to be done for every event A separately. So there's not a classification of events. It's a classification of events relative to other events. So you could also put this in the following form that you say, because only the differences enter here, you can say that the connecting vector from the event A to the event X is time-like, space-like, or light-like, respectively. Yeah, so it's not a property of the X itself. It's something which has to do with the difference, or in geometrical terms with the vector, which connects the two things. Okay, we will use these words time-like, space-like, and light-like frequently in the future. So let me talk a little bit about simultaneity and synchronization. Actually, we have already done a little exercise yesterday in the tutorial, the last one, where was about Einstein's synchronization procedure. And that's how we define a simultaneity in special relativity. And what I want to emphasize now is that this notion of simultaneity is relative. And actually, that's the reason why the theory is called relativity theory, because simultaneity is relative. That's why Max von Laue introduced this name, relativity theory, in 1909, I think. So the name comes not from Einstein. He adopted it only later. So let me talk about relativity of simultaneity. Difficult word, simultaneity. And that's something we have already touched upon yesterday. Confer problem, I think was the last one, number 4. On worksheet 1. So what we discussed yesterday was the following. We considered a particle which is at rest at the origin in one inertial system. So the world line of this particle is just the x-naught axis. And then we introduced a certain procedure. Well, not we introduced it, Einstein introduced it, and that's why it's called Einstein's synchronization procedure. We want to say what we mean by the statement that this event, let's call it A, that this event is simultaneous with a certain event on this world line, with respect to this world line. And this was done in the following way. We considered the light rays which pass through the event A, the light cone. And geometrically it's fairly obvious. There's one intersection to the past with this world line here, and there's one intersection with the future. If I consider the whole light cone of this event A, then I see there's one intersection to the future of A with this world line and one to the past. I think it's geometrically obvious. And this means there's precisely one light signal from the world line in the origin to the event A, and precisely one world line from the event A to this world line. So we may think of this observer who sits on this world line sending this light ray here, and in the event A, there's a mirror which reflects this back to the observer. And now we can measure the times here. We can read from the axis the time values. Here's the x-naught values, which are just the times up to the factor c. And we take the algebraic mean of this. Yeah? We add them together and divide by half. And then we get something here. So we do it in such a way that this time interval is the same as this here. That's precisely what we did yesterday. And now we say this event is simultaneous with this event here. That's the way in which the construction is done. Yeah? You measure the time of this event, the time of this event, and you take the algebraic mean. And that's the event which is supposed to be simultaneous with A. And we talked yesterday about what is a set of all events which are simultaneous with the same event here. So I now do this construction for all events. Off the world line, of course. For events on the world line itself, it doesn't make sense because this construction cannot be done. But for all events off the world line, it does make sense. And we get the hyperplane perpendicular to, it should pass through the point A, sorry. We get this here. And this here is precisely, of course, if I'm sitting in a coordinate system, in an inertial system where this is the x-naught coordinate, then this is precisely the hyperplane x-naught equal constant. So it's a three-dimensional hyperplane. Yeah? It's parameterized with x1, x2, x3. And these are the events which are simultaneous with this event here with respect to this world line. So in this inertial system, let's call this inertial system sigma. In the inertial system, sigma A is simultaneous, according to this construction, this radar construction, is simultaneous with this event here. Let's give a name to it. Let's call it B. With B. And now we do the same construction with respect to an observer which is moving with respect to this here. So it defines another inertial system. Yeah? So my old inertial system had this axis here, x0. And now I introduce another inertial system. Inertial means the observers who are at rest are moving in straight lines. So what can happen is only that this has a certain angle, which must be smaller with respect to the vertical than 45 degrees. And let's denote the coordinates in this new system with a twiddle. And now we do precisely the same construction for an event A here with this word line. So now I have to admit light signals from this word line. So I consider now an observer who is at rest in the twiddled system. So just to remind you, here I had my event B, which was perpendicular in the original, which was simultaneous with A in the original construction. And now I do it with respect to this construction here. My drawing is not very good. If I do this, let me see. Why looks this so funny? Actually, if I look at the picture, the point which is simultaneous would be here, right? If I divide this into two equal halves, but it should be lower than B. So for some reason, my picture is bad. What did I do? Let me try to copy the old one and then introduce the new axis again. So the old one was like this. Here was the x0 axis. Then I had here the hyperplane perpendicular, and here was my event A. And the light rays were this, under 45 degrees, right? And here was the event B. Okay, and now I introduce a new axis. Maybe it's a good idea to do the intersection point here. So that's x0 twiddle. Yeah, now it's better. You see, if I extend these things here, then that's the event from which a light signal from A is received, and that's the event to which a light signal to A is sent, right? And now if you divide this again in two equal halves, then you get something which is here. So this would now be a distance, a temporal distance, delta x0 twiddle, and it's supposed to be the same distance, delta x0 twiddle, and here would be the event B tilde, which is simultaneous now with respect to the new inertial system. And if I do this for all points here, I get something like this. So this is the hyperplane. x0 twiddle is equal constants. And you see in the picture it's not perpendicular. In the coordinate picture it's not perpendicular. If this is the angle alpha here, this comes up with the same angle alpha. So it's like the two blades of a scissor. Well, one blade is one-dimensional, the other one is three-dimensional. But otherwise it's like the two blades of a scissor. Doesn't look very nicely. I produce a nicer picture for the lecture notes. But I hope you got the idea what I was doing, yeah? So I considered these light rays here, and then I divided this interval into two equal halves. And then I connected this. And if I do this for all possible events A, I get a hyperplane, which in the picture is not perpendicular to the x0 twiddle axis. So in this new inertial system, let's call it sigma twiddle. A is simultaneous with B twiddle, and obviously not with B. So simultaneity is relative. Yeah? So that's, I said already, that's why the whole theory is called relativity theory. Actually, you often hear the sentence that according to Einstein's theory, everything is relative. I remember a feature in TV, Arte or something like that, actually to some part a fairly good feature on Einstein. It was subtitled, Alles ist relativ, everything is relative. And during this feature, it was even said, we learned from Einstein that everything is relative. That's complete rubbish. It's not everything relative according to a relativity theory. Simultaneity is relative. But there are other things which are absolute. The light cone is absolute, for instance. So what relativity does is that it replaces things which were assumed to be absolute in older theories, replaced it by other things. But it didn't give up absoluteness completely. So I think that's quite important. Let me write this down somewhere. So the absolute element in relativity theory is a light cone. And therefore we give up the simultaneity of the relativity, the absoluteness of simultaneity. So in Newton's theory, it was just the opposite. Their simultaneity was absolute, and the light cone was relative. And in relativity, in special relativity, the light cones are absolute, and simultaneity is relative. There are other things which are absolute. Acceleration, for instance, is absolute. Yeah. If a body is force-free, this means if it's not accelerated, or if there is a force acting so that it is accelerated, this has an absolute answer. All observers agree about this. In the first case, it's a straight line in space-time. In the second case, it's not a straight line in space-time. That's absolute. And there are other things which are absolute. Okay, so let me write this down. So in Newtonian physics, simultaneity is absolute. So if you consider Newtonian physics in a space-time setting, which is perfectly well possible. It's not usually done, at least not in elementary courses, but it can very well be done. You can write Newtonian physics in this four-dimensional space-time language. Then the absolute element, which determines the geometry, is a slicing into hypersurfaces of simultaneity. That's something absolute, where all observers agree about. And in relativity, in special relativity, I should say, the light cones are absolute. So one element of absolute of an absolute element, one absolute element is replaced by another one. Okay, this relativity of simultaneity, of course, has a number of consequences. In particular, it has a consequence that we have to require that signals are not allowed to move faster than light. I will show this in a minute. That's not a postulate of relativity. Yeah, the postulates were the relativity postulates which characterizes force-free motions, and the fact that the light cones are absolute, that the speed of light is absolute. But nothing in the postulate said that signals cannot move faster than light. That's something you can derive. And the way in which you derive it is that you find out that if you do not require this, then you violate causality. And you don't want to violate causality, so that's the reason why we assume that signals cannot move faster than light. So let me work this out now. I think most of you have seen this before, but I think it's a good idea to recall this. So actually it's a consequence of this construction, this relativity of simultaneity. So the limit character of the speed of light can be derived in the following way. So let's assume for the time being that it is possible to have signals which move faster than light. Then I will construct a contradiction with causality. So I construct something where the cause is not preceding the effect, but it's the other way around. Yeah? And the way in which I do this is the following. So I have one observer here. Let's say that's the world line P. And so that's the set of all events which are which have the same time, so which are simultaneous with respect to P. And now it's fairly obvious that I can construct causality violation if I allow to send signals in the past. So if I allow that this observer could send a signal into his own past, then I can easily construct violations with causality. But I will demonstrate that I can also construct a violation of causality if I allow this observer only to send signals into the future, but with a speed bigger than the speed of light. So I will allow for a moment that it's possible to send a signal of this sort. That's a signal which goes into the future in the sense that the time coordinate for this observer is increasing, right? So everything above this hyperplane has a bigger time coordinate than this event, and everything below has a smaller time coordinate. So the time coordinate is increasing here. And now let's assume that there's another observer, an assistant, with a world line Q, who has his own hyperplane of simultaneity, of course. It should be a straight line, of course. My diagrams are really not nice, I'm aware of this, but I try my best. So this was a construction that the hyperplane of simultaneity comes up in the following way, that this becomes something like this here. So these events are simultaneous with respect to Q. And if I allow again for this other observer to send a signal into his own future, this means it must be above this hyperplane, but with superluminal velocity, then it could send a signal like this. So this was the first signal. Let's call this L1. And this is the second signal, L2. And both together go into the past of this observer. Yeah? So the construction was like this. So P sends, so assume, P sends future directed, not in the past directed, but future directed, but superluminal, faster than the speed of light. Signal L1. Now Q sends, for his again future directed, but again superluminal signal L2. And combination of both give a past directed signal. And that obviously violates causality, right? So we could do the following. Well, let's begin with a harmless example. P is watching a lottery draw. Yeah? He watches the draw here in this event on Saturday evening. He jots down the numbers which are drawn. He sends this signal to his friend. The friend sends a signal back. And he hands in the lottery sheet with the correct numbers on the Friday before the draw was done, right? So you would always win in the lottery if you were able to have such, to send the signal. So that was a harmless example. There are more drastic examples. You can think of this as the event where this observer is born. And when he is grown up, when he is 20 or 25, he sends a signal to his friend, gets it back, and this signal kills the parents of this person before he was born. Yeah? Because that's to the past of the birth now. So with this signal, he could kill his own parents before he himself is born. And obviously that's a violation of logic thinking, right? That's the reason why we believe that causality, that it should not be possible to send signals into our own past. And the only way out of this is, on the basis of the formalism of relativity, that we prohibit signals which travel faster than light. Because this construction doesn't work with signals which always nicely stay inside the cone. You can try it. Yeah, it works only with signals which are faster than the speed of light. So that's the reason. So in order to preserve causality, we require that superluminal signals are not allowed. And if they ever will be detected, then relativity is in trouble. Actually, I think you all know that half a year ago, people claimed that they had discovered such superluminal signals. Yeah, these opera people, they claimed that with their experiment they had sent neutrinos at a superluminal speed from one place to another. Actually, when this message, when this came out, more or less everyone said there's probably something wrong with the measurement, and actually it was a little bit audacious by these people that they have gone to the public at a state where it was not really checked carefully. And I remember on BBC that Jim Al-Khalili, he is the British equivalent of Harald Lesch in Germany. So he's the person who explains via BBC physics to the public. That he said immediately after the experiment on BBC TV that he would eat his boxer shorts when this experiment turns out to be correct. And that was a reaction of more or less everybody who was right in his mind. But nonetheless, it caused a big discussion, and several people thought really that now physics is in big trouble. And the outcome was, of course, what everybody accepted, that a very trivial mistake was found, yeah? That the cable was loose, and that's the reason why the measurement was incorrect. And two of the responsible people for the experiment from the opera team had to step down because they found themselves embarrassed so much by this. So actually now everybody is convinced that to the present date nobody has ever seen a signal which moves at a superluminal speed. And don't get me wrong, of course you have to be always open. You should never be prejudiced against the outcome of experiments. But if an experiment really brings physics into big trouble, you should take it serious only when it has been checked and double-checked and triple-checked, and not jump on it immediately and come up with wild explanations. So that's what I wanted to say. So according to everything we know until now, there's no problem with relativity. This fact that superluminal signals should be forbidden seems to be realized in nature. Of course, it's only about signals. I should emphasize this. Nobody says that velocities, quite general, are impossible, which are bigger than the speed of light. For instance, there's a well-known example. If I have a laser beamer and I move it in this way, then the spot on the screen at a certain distance can move with arbitrary speed. Yeah? So if it's sufficiently far away, and if I move it sufficiently quickly, it can move at any speed, much bigger than the speed of light. But that's not a signal from this part of the screen to this part of the screen. Of course, it's a signal from my position to the screen, but not from there to there. Yeah? So somebody standing at the left-hand side of the screen could not send a signal in this way to a person standing at the right-hand side of the screen. Yeah? He would have sent a signal to me first, tell me how I should move my laser beamer. And this signal would, of course, take so long that everything together would move with subluminal speed. Yeah, but you would get an object which moves in a certain way, and it moves with superluminal speed. So there's nothing wrong with that, as long as it is not a signal. Another well-known example is two sheets of paper on a certain angle, and I move one of it up or down. Then the intersection point can also move with arbitrary speed. If I make the angle small enough, actually the speed with which the intersection point moves can be arbitrarily large, can be bigger than the speed of light. But again, that's not a signal from here to here. Yeah? It's not somebody sitting here sending a signal up there. So again, that's a sort of velocity which is bigger than the velocity of light, which is very well possible in nature. And where there are other examples, I think everybody knows that phase velocities can be bigger than the speed of light. That's quite frequent. Phase velocity in a plasma is always bigger than the speed of light. Yeah? The group velocity is always smaller, and the phase velocity is always bigger in a plasma. So again, that's something which cannot be used for a signal, because this phase surface is something which doesn't carry information, doesn't carry a signal. Actually, there are persons who claim that they have sent signals with superluminal velocity through a waveguide. There's a famous person here in Germany, in Köln. He's a retired professor now. His name is Nimtz. Maybe you have read in the newspapers about him. He claimed a couple of years ago that he could send a Mozart symphony through a waveguide with superluminal speed. And there were lots of discussions about this. So I was on conferences where he demonstrated this experiment, and we discussed with him for hours and hours. And I think everyone except himself is convinced that he did not send the Mozart symphony with superluminal speed. But it's quite clever the way he did it. But I think it's not a violation of special relativity. The essential thing is, how do you define the propagation of such a signal? And he does it in a funny way. He does not use the front of the signal, which in my view would be the most natural thing. Yeah? Really where the signal begins, the front. This is really a signal. If this arrives, then I say, aha, now something has happened. That can be used as a signal. He defines the propagation speed in a different way, in a tricky way. And I think that's a crucial point. So I doubt that he was actually able to send Mozart symphony at superluminal speed. Okay, so much for a little bit of space-time drawings, space-time diagram drawings, and concluding a couple of things just from geometric constructions. Up to now, we haven't calculated anything, right? So now we should begin a little bit to calculate. And for that, we need a certain formalism, which I think most of you have seen before. But maybe not everyone has really practiced it over in the next tensor. That's the so-called index calculus, where we juggle around with indices. So that's what will be our business for the rest of the term to a great extent. So I will now introduce this index notation for special relativity. I do it step by step, fairly slowly. So I will not develop the full apparatus of tensor calculus at the beginning. I will come to this later. So I will give precise definition of what a tensor is and how the calculations work, what sort of operations we can do with tensors. But for the time being, I will begin with a sort of hand-wavy introduction of this index calculus. And then when maybe we have become a little bit familiar with this and feel a little bit more comfortable, then we will do it in a more mathematical, technical way. Okay, I think this will be section 2.2 now. Which is index calculus, or let's say index notation for special relativity. So my conventions will be like this and the following. Greek indices. So that's something like mu, sigma, tau, or whatever. Any Greek index will take values 0, 1, 2, 3. That's our convention. So for instance, the coordinates, which up to now I have written in this rather lengthy way as a quadruple, x0, x1, x2, x3 of an event in an inertial system. Are simply denoted x mu now. So if I write an event x mu, this is just a shorthand notation and shorthand expression for saying an event with a coordinate x0, x1, x2, x3 in my chosen inertial system. And then we will have Latin indices occasionally. I will usually take them from the sometimes from the beginning, sometimes from the middle of the alphabet. So let's say A, B, C, or whatever. These Latin indices will take values 1, 2, 3. So the three spatial values. For example, the spatial coordinates. Only x1, x2, x3 of an event in an inertial system. Will be denoted xi or xa. And then we will introduce something which at the moment might occur to you somewhat unmotivated, but you will see in a minute that it's very helpful for doing calculations in relativity. That's what we call the Minkowski metric, or rather the coordinate expression, the matrix which represents the Minkowski metric. But we define it is something which has Greek indices. So the Greek indices take values 0, 1, 2, 3, and it's defined in the following way. This is supposed to be -1, 0, or 1, depending on the following. If mu equals 0, equal mu is 0, so the naught component is -1. This is true for all non-diagonal elements, and +1 we have if mu is equal to nu but not 0, so it's either 1, 2, or 3. So in matrix form we can write this in the following way. So you see it's something quite similar to the Kronecker delta, right? The Kronecker delta would be defined by this here without the first line if just the values 1, 2, and 3 were possible. Yeah? And here we have a -1 in one place. That's the difference to the Kronecker delta. And we will see in a minute why we do this thing, why we introduce this with a minus sign. So in matrix form, we could write eta mu nu as a matrix. So by this bracket, I mean the matrix with the components eta mu nu. So this would be like this. If I label the rows and the columns of the matrix in the order 0, 1, 2, 3, 0, 1, 2, 3, then I have here a -1. Here I have 3 times a +1, and everything else is 0. So you see it's the same as a Kronecker delta with the exception that here I have a minus sign. So I call this thing, this matrix, or this this arrangement of numbers, or whatever you want to call it. I call this the Minkowski matrix. That's actually an abuse of notation. Or one should say what I've written down is a representation of the Minkowski metric in coordinates in one chosen inertial system. But it's a special, it's a usual terminology in special relativity, just to call it the Minkowski metric. So why do we introduce this? Well, the reason is that relevant equations can now be written in a convenient way. In particular, the equation for the light cone can be written in a convenient way. So let's do this. Let's write the equation of the light cone with the help of this eta symbol. No. Then the equation of the light cone well, let me remind you how I've written it before. I've written it before in this way. X0 minus A0 squared is x1 minus A1 squared plus x2 minus A2 squared plus x3 minus A3 squared. Now I can take this to the other side and it becomes a minus sign. And for these differences I just write delta x. Yeah, so I can write it in this way. So I take this to the other side, so I have a 0 here. And then I have minus delta x naught squared. By this I mean this expression, yeah? X naught minus A naught is now written as delta x naught plus delta x1 squared plus delta x2 squared plus delta x3 squared. And this can be written now with the help of this eta symbol. You see? Because I have here 1 minus and 3 times a plus, that's why I introduce this thing in this way, with 1 minus and 3 pluses. Because now I can write it just as, well, that's a summation now. So I have 2 sums, 1 over mu from 0 to 3, and 1 over nu from 0 to 3. Eta mu nu delta x mu delta x nu. So let's check this. So what do we get when we let's calculate from the bottom to the top. So let's start with this expression and let's see if it really is this here. So you have two sums. So you see the eta is 0 if these two things are unequal. Yeah? So I only get a contribution if these two things are equal. So I have only 4 terms. I have the terms when both are 0, when both are 1, when both are 2, and both are 3. When both are 0, I get a minus sign here. Aha, that's this term. Yeah? When both are 1, I get this term. When both are 2, I get this term. And when both are 3, I get this term. So it's indeed the same thing. So that's the way in which the equation of the light cone can be written with this eta symbol. You see, it's fairly, the expression on the right-hand side is somewhat similar, or you can also look at this expression here. It's somewhat similar to the way in which you calculate distances in Euclidean geometry, right? The difference is that in Euclidean geometry you have a plus here. So it's not Euclidean geometry what we do here. Some people call it pseudo-Euclidean geometry. And pseudo refers to this minus sign here. Yeah? So it's similar to well, for a Euclidean product, I would have a Kronecker delta here. Yeah? That's the way in which you calculate scalar products in elementary linear algebra. So that's in the Euclidean coordinates. That's just with a Kronecker delta here. So here we have this minus sign, which gives this completely different geometry. We get a cone instead of spheres, hyperspheres, right? So one of the dimensions is distinguished from the other one. And now you also see what I mentioned last time already, why some people introduced the imaginary unit in the time coordinate. So I briefly told you that some people define x naught not as ct, as we do, but as ict, where I squared is minus 1. And you see that was killed this minus sign here. Then you would have pluses everywhere. And it would look like a Euclidean product. But actually it isn't, because one of the quantities is imaginary and the other 3 are reals. So it's just hiding the true geometry, and that's the reason why people nowadays don't do this anymore. But in older books you will find this I in the temporal coordinate. So that's why we introduce the eta, because we want to write the light cone equation in a simple way. So what I've said already, I might write here. So confer Euclidean. Is this spelled with a capital E? Yes, I think so. One should do this. Euclidean scalar products. And this is just with Kronecker. Delta mu nu instead of eta mu nu. So we are doing something which has some formal similarity to Euclidean geometry, to geometry with the Euclidean scalar product, but it has a minus sign in some place where there's no minus sign in Euclidean geometry. Okay, so this makes the equation for the light cone already nicer than the original way of writing it. We can even make it shorter. And you see here that the indices mu and nu appear in the following way. One index is a superscript and one is a subscript. And things are arranged in such a way that always such combinations occur. We will later talk about contravariant and covariant tensors, and then you will understand maybe a little bit better that there is a rule behind this. So at the moment it is just an observation that we have an expression where mu appears twice, once as an upper index, once as a lower index, and the same for nu. And these are precisely the things which are summed over. And that's something which occurs very often, and that's what Einstein prompted to introduce something which is called the Einstein summation convention. I write it down in a minute. I say it just in words. In words, it just says that whenever an index occurs twice, once as a superscript, once as a subscript, it's tacitly to be summed over. So we don't write the summation signs. That's Einstein's summation convention. I write it down in a minute. And actually, Einstein used to joke that this was his only contribution to mathematics, that he invented the summation convention, which makes all these formulas indeed much shorter. So from now on, we use Einstein's summation convention. So it says, actually it has two parts, over Greek indices that appear twice. Once as a superscript and once as a subscript. It is to be summed from 0 to 3. So we write this formula from now on in the way that we just omit the summation signs. It's tacitly understood that there is a summation involved. And there's an analogous rule for Latin. The same holds for Latin indices. But the sum, of course, is only from 1 to 3. Because it's our convention that Latin indices only take these values, 1 to 3, only from 1 to 3. So the equation for the light cone becomes what? Yeah, it's this equation, but now written without the summation sign. So we simply write it in this way. Brackets are not absolutely necessary, just for clarity. So I said already that other people use other conventions. So some people use Greek and Latin indices just interchanged. I already mentioned that some do not label the space-time indices from 0 to 3, but rather from 1 to 4. So they have the time in the end. You have to be careful when you compare different books. You have just to look up which particular conventions this author is using, and then you have to adapt this convention. And there's also an ambiguity as to the sign of the eta. You see, if you want to have the equation of the light cone written in this way, of course I could have replaced eta by minus eta. Because I have a 0 here, this would be the same. Yeah? But actually some people do this. Some people have here +1, -1, -1, -1, instead of what I have here. It's again a convention. And of course, this brings in sign changes in various equations. So you have to be very careful with the signs if you compare formulas from different books. It's quite common that different authors have different signs. And the reason is usually that they have different conventions. So one has to be careful about this. Okay, so this was... so in this way, I will use the summation convention and the index conventions for the time being. Later, I will also introduce something additional. Maybe I should write it already now. So if you've seen it, that you have seen it already, but I will use it only later. When we talk about electromagnetic fields and relativity, then I will extensively use the following rule. I will also introduce an eta with upper indices. And I will use both etas for pulling indices down or pulling indices up. So I should write this already now so that you have seen it. Although I will not use it for the next 60 minutes or so. Not today, I mean 60 minutes in the whole course. The eta with upper indices will be introduced as the inverse matrix of this. Maybe I should leave this on the board and just write here. So I can invert this matrix eta, and you see immediately that it is inverse to itself. So the inverse looks exactly the same thing. Yeah? If you multiply this matrix with itself, then you get the unit matrix. And I think you can do this in your head. I don't have to write it down. So later we will use we will introduce eta mu nu with upper indices as the inverse matrix of eta, let me use other indices here, or sigma for instance. What does this mean? Well, with our summation convention, we can write this condition now in the following way. Matrix multiplication means that there is a sum over neighboring indices. Yeah? This is a mu row component of the matrix, which results from multiplying this matrix with this matrix. Yeah, remember how matrix multiplication is done. You multiply terms, and you multiply them in such a way that the row here is multiplied with the column here. So neighboring indices are summed over. So that's the mu row component of this matrix product. And if that's the inverse, then this must be the unit matrix. And the mu row component of the unit matrix is, of course, delta mu row, the Kronecker. Yeah? So that's the condition which defines the eta mu nu. That's the way in which it is defined. So as a matrix, we have exactly the same expression. We have eta now with the indices up. It's just exactly the same matrix as this here. -1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Yeah, if you multiply this matrix with this matrix, quite trivially, you get +1, +1, +1, +1 in the diagonal, and everything else 0. So I will later use this eta with upper indices, and I will also use both etas for raising and lowering indices. That's something which is extensively used in relativity theory to make formulas shorter. Some of them will still be long enough. So we will use both things, the one with the lower indices and the one with the upper indices for, no, the other way around, lowering and raising. So for instance, if we have something with an index, with an upper index, say an expression v row, expression which depends on an index which takes values 0, 1, 2, 3, and we multiply it with the eta in such a way that here is a summation. So that's the same index. Then we get something which has an index down, right? Because this is summed over, so it's gone. The whole thing has just one index down. And that will then be denoted v mu. Yeah, with the same kernel symbol, but now with a lower index. So the same thing also works the other way around. If we have something which begins with a lower index, then we can use the eta with the upper indices to raise the index. So here we get w mu. Again, the summation is over neighboring indices. So that's something we will extensively do later. But for the time being, I will write out the eta. So of course, this allows to simplify expression in the way that whenever an eta occurs, we don't have to write it. Yeah? We just pull the corresponding index. And then the eta is gone. It's no longer seen. But for the time being, I will write the etas out so that we become familiar with this step by step. I just wanted to mention it so that you are prepared when this will be introduced. Okay, we will talk about orthogonality with respect to the metric, I think, on the next worksheet. I think I do not do this at the moment here. So I think it's better to discuss this first in connection with a certain problem. So we can now talk about Lorentz transformations a little bit. So we can use this index juggling in order to write down some basic properties of Lorentz transformations. I think you have all heard about Lorentz transformations. So this will already be section 2.3. Named after the famous theoretical physicist Hendrik Anton Lorentz from the Netherlands, who was an older friend of Einstein, and he was strongly involved in the development of relativity. So actually many essential formulas in relativity were introduced by Lorentz first. And many things are named after him, as you know, the Lorentz contraction and things like that. But actually Lorentz didn't have the correct interpretation for the formulas. He had many formulas before Einstein, but Einstein provided the correct interpretation for them. So it's certainly not correct to say that Lorentz invented relativity theory in any sense of the word. He had the formulas, but not the physical interpretations. So in particular, he introduced what we call Lorentz transformation as the invariance group of something which occurred in connection with these formulas. Let me write down the definition, and then we discuss what Lorentz transformations actually do. So they are defined with in relation to this Minkowski metric. So the Lorentz transformations are just the linear transformations on a four-dimensional space which leaves this eta invariant. So it's a transformation. It's a set of all transformations which leaves this eta invariant. It's a symmetry group of this eta. So we define Lorentz transformations in the following way. So that's the definition now. A Lorentz transformation is a linear transformation of my four coordinates x0, x1, x2, x3. So linear transformation means I can write it in the following way. So if I have my x mu's, my coordinates in the system I start with, I make a linear transformation. This means I multiply this with a matrix. That's what linear transformation means, right? And let me write this as in this way. The summation is over mu, and here's the second index row. So these are the components of a matrix which is applied to this x mu, which you may think of as a row vector, as a column vector. Yeah? And so this gives you something new, which will then be denoted x row twiddle. So it's a transformation which makes your coordinate quadruples x0, x2, x1, x3, x0, x1, x2, x3 into another one x twiddle node, x twiddle 1, x twiddle 2, x twiddle 3. And it should, in addition to being linear, it should satisfy another property, the linear transformation, such that the eta is invariant. So if I do the following, if I multiply the matrix in such a way that once there's a summation over this index and once over this index. So in both cases it works over the upper index of the L. So I need the eta with the lower index. Then this should be the eta rho sigma. That's the definition. So that's what one expresses in mathematics in the form that one says that's a set of all transformations which leaves this thing invariant, right? So I transform each index with this transformation, and I should get the same thing I started with. So it's left invariant. So that's a formal definition. Why is this set of transformations interesting? We can then prove, and actually we will do this, it's quite simple. We can then prove that the Lorentz transformation maps an inertial system to an inertial system. So the claim is, if these are the coordinates in an inertial system, and I make this transformation with an L which has this property, then I get new quadruples for any event. And the claim is that this new system, this new coordinate system, is again an inertial system. So what do we have to prove? Remember what inertial systems have to satisfy? There were two postulates, right? I call them P1 and P2. The first thing was that in an inertial system, all force-free bodies move on straight lines in space-time. So if the claim is true, what I've written here, then this transformation must map straight lines onto straight lines, right? Otherwise it wouldn't be true. But it's obvious because it's a linear transformation. Clearly, every linear transformation maps straight lines onto straight lines, right? And the second postulate was that, I can now phrase it in the way that I say the light cones are invariant. In every inertial system, the light cones are given by these cones under 45 degrees. So the transformation must leave the light cone invariant. But that's again true, because the eta is invariant, and the eta determines the light cones. So let me write this down. We have to prove. We have to verify. Let me write it in this way. That a Lorentz transformation maps straight lines onto straight lines. And actually there is nothing to prove. I just write clear from linearity. If you have a map of this form and you consider all four tuples which lie on a straight line, then the images will also lay on a straight line, because this is a linear transformation. And the straight lines, clear from linearity, and that the light cones are left invariant. And again, this is clear from what? If I write eta mu nu, well, actually I should write it with differences. So let me just put it this way. So what is this? If my x mu's are constructed in this way, then of course I can draw the L out of the difference sign, right? Because if I apply this to a difference, then I get the difference of the two results because of linearity. So I can write this here as eta mu nu. So this here is now L with an upper index mu, rho x rho, delta x rho, sorry. The board is always too short. And this is L with an upper index nu, lower index tau, delta x tau. So I hope you can read this. Yeah? And now we are almost done, because now you see you have here exactly the expression which enters into the definition of the Lorentz transformation. So I can continue here. Well, actually, I can do this here. We are almost done. So if I continue here, then I have just, what are the indices? Eta rho tau. Delta x rho, delta x tau. You see, if I'm on the light cone, then this here is 0. And then I'm also on the light cone. Then I get the same expression for the twiddled coordinates. So the equation for the light cone is left invariant. This here is 0 precisely if this here is 0. So the light cone has the same equation in both coordinate systems. That's what we have to prove. So I can close the bracket here. So that's the proof of the second statement. So Lorentz transformations indeed map inertial systems to inertial systems. Now comes a interesting question. Are these the only transformations which map inertial systems onto inertial systems? What do you think? Or are there more transformations which leave straight lines invariant? So they map straight lines onto straight lines and leave the light cones invariant. These are the two conditions we have to check. Well, it's a linear transformation. Linear means in particular that it leaves the origin invariant. Is this necessary for such a transformation? Yeah, if this is 0, then this of course is also 0. So the origin of the coordinate system, of this coordinate system, is the same as the origin of this coordinate system. But the origin is completely arbitrary. I can choose it wherever I like, right? So I could just shift the origin in space-time to any other point. Then I get a bigger group of transformations. They're called Poincaré transformations. Yeah, which add to the Lorentz transformations, just a shift of the origin. So let me write this down. So they are not the only ones. Actually, there's still another possibility to generalize it. Maybe you can think about it during I clean the board. Maybe what else you can do. Instead of applying a Lorentz transformation and shifting the origin, can you do anything else without violating the property of having an inertial system? So Lorentz transformations are not the only transformations that map inertial systems to inertial systems. So the first generalization we could consider are the so-called Poincaré transformations. They are sometimes called, AKA means also known as, maybe I should write it out, also known as inhomogeneous Lorentz transformations. Shift the origin. In addition to what a Lorentz transformation does. So they are of the following form. The new coordinates x mu typical are constructed from the old one by a Lorentz transformation. And then I add just an a mu which shifts the coordinates. And it's easy to check that these two statements are still true, that straight lines are still mapped onto straight lines Yeah, this doesn't change this property, this inhomogeneity. And the light cone is also left invariant because if I form differences of coordinates, then the A mu drops out, right? So the second property is exactly the same as it was before. So Poincaré transformations are also have the property of mapping inertial systems onto inertial systems. And now, anybody got an idea what else I could do?
Constant angular shifts.
Angular shift, what do you mean by that? Räumliche Drehung, spatial rotation. What was the other thing? You can do this, that's true. But is it really something more general than a Lorentz transformation? Well, spatial rotations are actually included in Lorentz transformations already. So we will see this, not today, but at the beginning of the next lecture. I will consider special Lorentz transformation, and the two special cases I will consider are spatial rotations, they are Lorentz transformations, and the Lorentz boosts, they are also Lorentz transformations. So that's not something which is actually additional. But what else could I do maybe? Think of the unit, somewhat rather trivial. I could stretch the axis. Yeah? I could stretch the spatial axis and the temporal axis with the same factor. If I do it with different factors, then the light cone would be deformed, right? But I do it with the same factor, then the light cones will be preserved. And a constant stretching factor, of course, also leaves straight lines invariant. So if I allow this additional freedom, then I get what is called the Weil group. It's named after the German mathematician Hermann Weil. That's the one with Y. There's also a famous mathematician with I. That's André Weil. That's a French mathematician. And sometimes they were confused. So when André Weil lived in California, some people refer to him as a wrong Weil, because people who wanted to see Hermann Weil, they actually met André Weil, which is of course a little bit unfriendly because both were quite famous. Maybe this is a more famous one, but also André Weil was a very, very important mathematician. So that's Hermann Weil, the German one. So that's Weil Trafos. So they change the units. In addition, they change the units, and by that I mean the space or the length and time units. The length and time units. With the same factor, with the same constant factor. So how does such a Weil transformation look like? So the shifting of the origin has nothing to do with the units. So the unit, change of the units refers to this factor here. So here I could do something like an e to the k. So I multiply with a positive number, with a constant k. And then I shift. So that's what we call the Weil group, the Weil transformations. Does anybody has an idea how many parameters I need in order to characterize a Lorentz transformation? So what's the dimension of the Lorentz group? Have you heard this already? Okay, we will do this next time. Actually, it will come out to be 6-dimensional. So Lorentz transformation, the most general Lorentz transformation is characterized by 6 parameters. Actually, it's 3 rotation angles, and it's 3 parameters which characterize boosts. So the Lorentz group is 6-dimensional. We will talk about this next time. And maybe now you can guess what's the dimension of the Poincaré and of the Weil group. So if this set of transformations gives the 6-dimensional set, how many dimensions do I get by this additional thing here? You're smiling already? Yeah, 4 extra, so it's 10 altogether, right? So the Poincaré group is 10-dimensional. And if I do this in addition? 1 more, so that's 11-dimensional. Yeah, so the Weil group is 11-dimensional. Then there's an even bigger group, maybe some of you have heard about, that's a conformal group. This is 15-dimensional. This is a group where I forget about the straight lines, where I just talk about the light cone. If I only ask about the transformation which leaves the light cone invariant, that's a conformal group, which plays an important role in high energy physics. Because for high energies, more or less everything is very close to the speed of light, so I can only, it's sufficient if I just consider the symmetry group of the light cone. So these are the important symmetry groups which occur in relativity. So if we really want to have the full symmetry, so not just the symmetry of the light cone, then we have to restrict where the biggest thing we could consider is a Weyl group. Yeah? But usually we fix the units. It's very uncommon to make to leave the choice of the units arbitrary. Yeah? So let's fix the units, then we restrict the Poincaré group. And the translations are rather trivial. Yeah? They don't do something really interesting. So one usually also keeps the origin fixed. And then we have just a Lorentz group to investigate. So if we take special relativity serious, which says that all inertial systems have equal rights, then we have to require that the laws of nature are invariant under Lorentz transformations. That will be our important guiding principle. And that's what special relativity requires. So actually it requires even invariance under these bigger groups. But with this restriction I've just said, it's sufficient to consider the Lorentz group. And we will talk about the Lorentz group a little bit more tomorrow. Okay, so tomorrow we meet at 2 o'clock, again in this room here, yeah? Okay, see you then.